Alright, the last type of quadratic that we have to solve is a quadratic inequality. So inequalities have intervals of solutions rather than just 2 points. So it's not just where it crosses the x-axis, but all of the points that will make the statement true. So there are many points that can make an inequality true. So for example, I've graphed this one. If f of x is less than negative x squared plus 4x. So here's the graph of negative x squared plus 4x. It's flipped, it's moved up 4. Less than meaning everything that was below that line. So all of these points in the shaded region are less than or equal to the function itself. So all of these points are solutions. So to solve these algebraically, you start by treating it like it's just a regular old equation. So we'll do the steps in this example. So the example we're going to use is x squared minus 2x minus 8 is greater than 0. So step 1, you factor it. If it can be factored, go ahead and factor it. Step 2, solve it like you normally would. So x has to equal 4 to make that part equal 0, negative 2 to make that part equal 0. These 2 points are your important numbers. So step 3 is we're going to draw a number line with your important numbers on it, and you're going to mark them. So I'm going to draw a regular number line. I'm going to mark negative 2 and 4 because those are my important numbers. They're going to be open circles because in my original problem it was not underlined. So just a greater than means open circles. Greater than or equal to would be closed circles. So after I mark my important points, and the end of the number lines would go from negative infinity to positive infinity, I'm going to test some points. I need to test a point that lives out here. I need to test somebody in there. I need to test somebody up here. So I'm going to test negative 3. I'm going to test 0. I'm going to test 5. So when I plug in negative 3 back into the original problem, so negative 3 would go in for where I see x, I would get that 9 plus 6 minus 8 equals 7. Is 7 greater than 0? Yes. So it works right there. That's a true statement. When I plug in 0, I get negative 8 is greater than 0. That's false. When I plug in 5, I'm back to 7 is greater than 0. That's true. So I go back up to my number line, or I drew a second one here, and I shade in the areas where it worked out. So my solutions are all the numbers between negative infinity and negative 2. So the set of negative infinity to negative 2. In combined with or union with 4 to infinity. So that's what it looks like. So without all the steps, here's another example. I have to use borrowing to factor this. After I factor, my important points are 1 and 7/2, which is the same thing as 3 1/2. I'm going to mark 1 and 3/2, and I tested 0, 2, and 4. So when I plugged in 0, that didn't work. When I plugged in 2, it did, because negative 3 is less than or equal to 0. And when I plugged in 4, that worked as well. These are closed-in dots because it's or equal to rather than just less than. So they're closed-in dots. So this didn't work, this did, this didn't. So the section between these two numbers is the solution set. So x is equal to 1 to 3 1/2, and I'm using closed brackets because they're closed-in circles.